Howdy ho everyone, and welcome to Logic Lecture 6. In today's lecture we're going to continue talking about first order logic. I remember that I said that a logic has two main components, being the syntax and the semantics. We covered the syntax quite comprehensively in the last lecture, and I'll begin just by recapping the main points from that lecture, and then I'll begin talking about the semantics, and in particular how we can give an interpretation to the function and predicate symbols in the first order language. So without any further ado, I think let's just go straight to the slides, and I will see you again at the end. Okay, so let's begin by just briefly going over the main points from the previous lecture. You'll remember that we introduced the concept of a first order language, which we use to write down our formulas. And a first order language consists of two sets, F and P, these guys here. And F is a set of function symbols, and P is a set of predicate symbols. Now remember that for every function in F and every predicate in P, they all come with a so-called arity, an arity being the number of arguments that that function or predicate takes. Next, we introduced the concept of a term. Terms are the things that appear as arguments of functions or predicates, and they're given by this inductive grammar. So a term T is either a variable x by itself, or it is a function symbol f which has some arity k, and it's applied to k terms t1 up to tk. So here we're kind of assuming that we can construct the smallest terms, which are variables, and then showing how to construct larger ones sort of inductively. Note that as a consequence of this definition, if the arity of a function symbol is 0, then it doesn't take any arguments, and that means, and of course then it's a constant symbol. So this definition also implies that any constant symbol by itself is a term as well. Next, we have a formula for grammars, and a formula A in the basic or atomic case is a predicate formula built from a predicate symbol P in the language, and that predicate symbol also has an arity, which I'm thinking here of as being K, and so a predicate formula is a predicate symbol P applied to K terms T1 up to TK. Next, we also have all the connectives from propositional logic. So we have negation, conjunction, disjunction, implication, and by implication. And finally, we have the two quantifiers for all x a, and there exists an x such that a. Now, when we have a quantifier, remember that we also had the concept of the scope of that quantifier. So essentially, the scope of this quantifier for all x is everything that's in the brackets between it. So really just this a. So this quantifier has the scope of this guy here, and the same for exists x. The scope of this guy, this quantifier, is a, or everything between the brackets here. And that gives us the concept of, if we have a variable occurring in a formula, we can say that it's either bound by a particular quantifier, or it's free, which means that it's not bound by any quantifier. So take an occurrence of a variable x, for example, then it is bound if it's falling within the scope of some quantifier for all or exists with the same name. So this quantifier here for all x binds all the occurrences of x in A. And if the occurrence does not fall within the scope of any quantifier of the same name, then it's called free. And that pretty much takes us up to the end of where we got to last lecture. Okay, so the main objective of today's lecture is to at least begin understanding how we can give a semantics or a meaning to all formulas in first order logic. Of course, That means we have to treat the simplest formulas, which are the atomic formulas or the predicate formulas, P of T1 up to Tk. Now, in order to understand whether a formula like that is either true or false, well, I mean, it really depends on the meaning of several things. First of all, we have to define the meaning of the predicate symbol P. And so we have to understand what the predicate P means, and we also have to understand what is meant by these terms. Now remember that the terms are constructed from function symbols and variables, and so we have to define what is meant by all of the function symbols in the terms, and also by all the variables occurring in the terms as well. Now, since even when the predicate symbol and the function symbols are fixed in terms of their meanings, the variables are still supposed to be variable. Today we're just going to concentrate on the idea of fixing the meaning of the predicates and functions occurring in a first order language. Which brings us quite nicely on to this guy here. This big egg is Humpty Dumpty. So for any non-UK students who might not be familiar with this, there's a nursery rhyme involving Humpty Dumpty. He sits on the wall, he falls off it, and then it proves quite impossible to put him back together again. And the character Humpty Dumpty also turns up in the well-known children's classic Through the Looking Glass by Lewis Carroll, and that's a sequel to Alice in Wonderland. One thing you might not know about Lewis Carroll is that it's actually not his real name, it's a pen name. His real name was Charles Dodgson, and he was a mathematician at Oxford University. And so, I mean, he did mathematics for a kind of day job and was probably much more successful, I would say, in his second job as a children's author. But you can see that quite a lot of his logical and mathematical ideas kind of come through a little bit in his literature as well. And so if you haven't read this book or Alice in Wonderland, I do recommend giving it a look. So anyway, in Through the Looking Glass, Alice, who's our heroine, goes through the magic mirror and meets a kind of array of colourful characters, including this guy, Humpty Dumpty, who's very kind of argumentative and, very awkward. And here's a quote from the book. He said, "When I use a word," Humpty Dumpty said in rather a scornful tone, "it means just what I choose it to mean, neither more nor less." Now, I chose this quote because I think it's quite relevant in understanding the concept of assigning a semantics to a first order language. Now, we have a set of function symbols and predicate symbols, but they are just symbols written down on a piece of paper. And although we have to respect the arities of those symbols, we are free to choose exactly what they mean. Here's a further example of this, from the same book. Lewis Carroll also put quite a lot of poems in his book, and here's a short passage from his famous poem Jabberwocky, which is a kind of a nonsense poem. "'Twas brillig, and the slithy toves did gyre and gimble in the wabe. All mimsy were the borogoves, and the mome raths outgrabe. Beware the Jabberwock, my son, the jaws that bite, the claws that catch. Beware the Jubjub bird, and shun the frumious bandersnatch." Now, if you're not a native English speaker, or even if you are, you might be thinking, the fuck does that mean? And understandably so, because in fact most of these words are not accepted words in English. They're completely made up. So, for example, the idea of something being brillig, it's kind of suggestive, perhaps, of being sort of like Twilight-ish or brilliant, perhaps, or slithy, which you might think of as being, as obviously a little bit like slimy or something like this. But they're not real words. But you can still see by the way they're used that they're obviously used to indicate properties of things. So brillig here you can kind of think of as being a predicate, even though it doesn't really have any accepted meaning in English. Now, of course, it means that whether we would be free to choose the meaning of this word, and we can, if we so wish. Again, these are just symbols written down on a piece of paper, and we're allowed to say what they mean. All right, so now let's start thinking about how we kind of how these ideas kind of map on to actually giving an interpretation of a first order language. So suppose that we have some first order language, sigma, which is the set of function symbols f and predicate symbols p. We are going to define the meaning of those symbols in something called a first order structure, which I will generally write using capital M or some variant of that. Now, the first thing we're going to do is we're going to pick some set of objects, D, which is called the domain, and you should think of that as the kind of universe in which we are understanding all the functions and predicates and constants, and we'll understand variables and eventually formulas inside that domain or universe as well. So, for example, my domain, I might pick the set of numbers if I want my formulas to talk about numbers. Or I might think about a different set, such as like the set of all students taking this class, or all the objects in my kitchen cupboard, or you know, every object in the known physical universe, or whatever we want. So first of all, we'll set the domain, and then second of all, for every function symbol, small f in the language, we're going to pick some appropriate function f superscript m in that domain. So in other words, when we have a function in the language, then it should get interpreted as a real function in that domain. So if I have, so for example, if I've picked a domain to be natural numbers, then fm should be a function on the natural numbers, and if it's if the domain is the set of students in the class, then fm should be some function which sort of on students in some sense. We have to, when we're interpreting these functions, we have to make sure that we respect the arity, so that if the function symbol is binary, for example, takes 2 arguments, then it has to be the function fm in the domain has to take 2 arguments as well. Similarly, predicate symbols P in the first order language, we pick an interpretation, a predicate or a relation in that domain, again of the correct arity. So, for example, if the predicate has arity 1, then we give it we interpret it as an arity 1 relation in the domain, which really means it's that we pick a subset of that domain is really what it means, or a property of objects in the domain. And if it's, for example, a predicate symbol of arity 2, like a binary relation symbol, then that should get interpreted as a binary relation on objects in the domain. And then if I write fm for the collection of all these little fm, and pm for the collection of all these relations pm, then the first order structure is the triple m, which is given by the domain D plus the set of all the interpretations of the functions in f, and the set of all the interpretations of the relations in p. So domain and real functions and real predicates or relations. This might seem a bit abstract, so let's see a concrete example. So here's an example that we gave in the previous lecture of a first order language for piano arithmetic. So this language has these function symbols, 0, s, plus, and times, and these 2 relation symbols, equals and less than. And this table just reminds us of the arity of all those symbols and their types. The symbol 0 has arity 0, so it's a special case where it's a function symbol, but it's a constant. And here I've reminded us of the usual meaning of these symbols. So for example, this symbol here is a predicate of arity 2, and it usually means that one thing is less than another in standard mathematics. And indeed, I think we can define a structure in which everything has the expected interpretation. So our interpretation, our first order structure for this language is going to be M, which has these three components. First of all, the first component is this blackboard style N, which is the symbol for the natural numbers. So the domain of the structure is the set of all natural numbers. Next, we have these, we had 4 function symbols in the original language. So for each of these, we have to give it an interpretation in the domain of natural numbers. So if we take 0, the symbol 0, then that's a constant, which means it has to get interpreted as a constant or an object in the natural numbers, which means a natural number. So obviously, I mean, the obvious interpretation is to interpret 0 in the structure M as being the natural number 0. We could interpret it as a different natural number, but interpreting it as 0 seems to make the most sense. Similarly, S in our language is a unary function symbol. It has arity 1. It's usually interpreted as meaning the successor function on the natural numbers. In other words, the function that takes a natural number and gives you the next one. So S of x equals S of x equals x plus 1. That's the way to interpret that. Again, we could have given it a completely different interpretation, but in this structure, I'm choosing to interpret it that way. Similarly, the interpretations of plus and times, they're both binary symbols, so they have to get interpreted as binary functions on the natural numbers. In other words, functions that take 2 natural numbers and return a natural number. And although I could pick any interpretation that I want, I'm choosing to interpret them as the addition and multiplication functions on natural numbers. And finally, we have 2 predicate symbols, equals and less than. They both have arity 2, that is, they're binary symbols, so they have to be interpreted as binary relations on the natural numbers. And so I'm going to interpret these as the equality and strict inequality relations on the natural numbers, respectively. So in this structure, I've just taken the language, I've set the domain to be the natural number and the set of natural numbers, and then I've just given all the symbols their standard interpretations, although I could have chosen to interpret them in a different way. And you can write down structures where 0, S, plus, and times all have whichever kind of meaning that you want them to have, with the only rule being that the arity must be respected. So 0m has got to be a natural number. It can't be a function or anything like that. And plus m and times m have got to be binary functions. They can't be functions that take 1 argument or 3 or 4. But apart from that, really anything goes. Remembering our Humpty Dumpty theory of language. Okay, so here's our second example. You'll remember that in the last lecture, I gave a first order language for songs in my MP3 library. And so I've just summarized them in a table here. I have some constants that represent songs or are intended to represent songs. I have a couple of unary functions, next and prev, which are supposed to indicate the next and previous song. I've got some predicates that represent genres, so I might have blues, reggae, pop, and so on. And I've got some binary predicates for comparing songs. So this triangle is a binary predicate, and it's supposed to mean something like X is better, one song is better than another. And this twiddle or tilde that means that is supposed to mean anyway that one song is kind of similar to another. So again, we can give a first order structure that captures this language or that interprets this language. And again, although I could pick any meanings for the functions and predicates, I'm going to pick meanings that correspond to their usual meanings as listed in this table. So we're going to define a first order structure, and remember that the first thing we have to do is specify the domain of the structure, or the universe in which we'll interpret everything. So I'm going to write my S for my actual song collection that I have at home. And then, of course, the functions and predicates are all going to get interpreted as functions and predicates on my actual song collection. So constants, for example, are going to get interpreted as elements of my S. So the interpretation, Lonely Avenue M, of the constant symbol Lonely Avenue, is going to be this song, Lonely Avenue, which was cut by Ray Charles on Atlantic Records in 1959. That's a pretty cool song. You should check that out. The function symbols next and prev are interpreted as the next and previous song functions, which I'll write as next M and prev M on my song collection. So I assume that I've got that all the songs in my S are written down in some order, and next M is the function that takes a song and returns the next one in that list, and we can imagine that perhaps it loops round if you get to the end, and prev M gives you the one before. And predicate symbols become relations of the appropriate arity on my song collection. So, for example, blues M will be the set of all songs in my S that have the genre blues, and this tilde symbol will get interpreted as tilde M, which I'm defining to be all the set of pairs of songs S1 and S2, such that S1 is similar to S2. So a way of writing a binary relation is just as a set of pairs, all the pairs that belong of things that belong to that relation. Yeah, and I think that's it. So we interpret constants as songs, as functions on songs, and predicate symbols as predicates or relations on songs. So hopefully by now you should be starting to get the idea. An interpretation for a first order language is called a first order structure, and a first order structure consists of three things. Firstly, a domain or a universe in which we interpret all the elements of the language. Secondly, an interpretation for each of the function symbols, which has to respect the arities of the function symbols. And thirdly and lastly, an interpretation for each of the predicate symbols. Now, what I'm going to do next is go back and give the definition of a first order structure in a bit more mathematical detail and try and make everything a bit more formal. For that, I'm going to need a few concepts from set theory, nothing too complicated, and I think probably you will have come across this already in the discrete mathematics course in the first term. But even if not, it's quite simple. And so first of all, I'll introduce the set theory concepts that we need to make the definition. Then I'll go on and give the formal definition of a first order structure. And lastly, we'll just show that the examples I've already given do actually meet that definition. So in order to give the interpretation of a first order structure, we're going to need two main concepts from set theory, and the first is the so-called Cartesian product of sets. Here's the definition of the Cartesian product of two sets. If x and y are sets, then we write x cross y for what is called their Cartesian product, which is defined by x cross y is equal to all the pairs x, little y, such that little x belongs to big X and little y belongs to big Y. So all the set of all pairs of elements from X and Y respectively. Now, of course, there's a special case of this where X and Y are the same. In that case, X cross X is the set of all pairs of elements just from X. And this can then be generalized to give a Cartesian product not just of two sets, but of k sets. And we're going to need this too. So, x to the power k is an abbreviation for x cross x cross x cross x, So the k times, so basically the Cartesian product of k copies of the set X, and that is equal to the set of all tuples x1 up to xk, so the set of tuples or lists of k elements such that all of the elements x1 up to xk belong to X. So hopefully that's simple enough. So the main thing we're actually going to use probably is this x to the power k when we're making the formal definition. The next thing we're going to need is the concept of a relation. So relations can have any arity. It can be unary or binary or ternary, which is 3, or quaternary, which is 4, or really or any arity at all. So a k-ary relation on the set X is a set R, which is a subset of x to the power k. And remember that x to the power k is the set of all k tuples of elements in X. So a k-ary relation is just some set of k tuples of elements that all belong to X. So here is some examples of relations on the natural numbers, which remember I'm writing this blackboard style n. So first of all, the set of all natural numbers n such that n is prime. Now that's an example of a oneary or unary relation on n, because it is a subset of n to the power 1, which is just n. Next, here's a binary relation. Many of the relations on natural numbers we consider are most naturally expressed as binary relations. So here is the set of all pairs of numbers m and n such that m divides n. So that's an example of a binary relation on the natural numbers. You could also think of many other examples of binary relations such that all the pairs m and n such that m does not equal n. For example, that's another example of a binary relation. And that is a set of, that's a subset of n cross n, which is the same thing as n to the power 2. Here's an example of a ternary relation. The set of all numbers m, n, and p, such that m times n equals p. And that's, again, an example of, it's a subset of n cross n cross n, which is the same as n to the power 3. And so, by definition, that is a ternary relation on the natural numbers. And finally, here is a relation of arity k plus 1. So the set of all numbers x1 up to xk and y, such that y equals f of x1 up to xk for some function f. So I imagine I have a k-ary function f, and then I can convert that somehow into this k plus 1-ary relation that kind of stores all the arguments of the function together with its result. And by the way, this shows that you can encode functions as relations at the expense of kind of somehow increasing the arity by 1, although not really, because I mean, obviously storing the result of the function is kind of the same thing as embedding it into this relation here. So anyway, that's not too important. What's important is that this is a subset of n to the power k plus 1. In other words, a set of k plus 1 tuples of elements of n. Okay, and so now with the concepts of Cartesian product and relations in hand, we can give the formal definition of a first-order structure of a first-order language. So, given a first-order language, sigma, which is a set of functions f and predicate symbols p, a first-order structure for that language is a triple of things d, fm, and pm, where first of all, D is a non-empty set, which is called the domain of that structure. Secondly, we have to give the definition formally of this curly FM. So the definition is as follows. for every function symbol little f in this big F up here, and supposing that it has arity k, then little fm has to be a member of fm, so there has to be an interpretation of the function f in this fm, which has to be a k-ary function on D. So that means that for every function symbol f in this in the first order language, there has to be an fm which has to have type dk maps to D. So in other words, this function fm takes in k elements of D, so a k tuple of things all from D, and returns an element of D. So for example, if f is a function symbol of arity 2, then fm has to map D2 or D cross D into D. So it takes pairs of elements from D and gives you back an element of D. By the way, in the special case where k equals 0 and therefore f is a constant symbol, then fm just has to be a member of D. The reason why technically is that when k equals 0, dk is the empty set. And giving a function from the empty set into D is exactly the same thing as just choosing one element of D. But you don't really have to worry about that. You can just remember that, that constant symbols get interpreted as elements of the domain. Finally, for every predicate symbol, P in curly P, and supposing that that predicate symbol has arity k, it must get interpreted, Pm, as a relation of arity k, a k-ary relation. So in other words, Pm has to be a k-ary relation on D, which means that it is a subset of D to the power k, and that means that it has to be a k tuple of elements all from D. So again, in the particular case where k is equal to 2, for example, then Pm has to be a subset of D cross D, or D2. So in other words, a set of pairs of elements in D. Now let's return to our example of piano arithmetic, where remember that I had taken as my domain the natural numbers in this structure M, and 0m, sm, plus m, and times m are just the standard interpretations. So 0m is the number 0, sm is the successor function, etc., etc. And similarly for these two predicate symbols, equals m is the equality relation on natural numbers, and less than m is the strict inequality relation on natural numbers. So we can just observe that this does meet the formal definition. The domain is a non-empty set, so it's a good domain. Natural numbers is definitely a non-empty set. Next, 0m is the number 0, which is definitely an element of the natural number, so that's fine. Sm, remember that it's the successor function on natural numbers, that takes a number and gives you back the next one. So it definitely has type n1, which is equal to n into n. So it takes a number and gives you back another number, so it has the correct type. Plus m and times m are just addition and multiplication on n, so they're both binary functions on the natural numbers, meaning that they take two numbers and give you back another number. So they have type n cross n into n. And equals m and less than m are both subsets of n cross n. They're binary relations on the natural numbers. So for example, equals m is the set of all pairs n and m in big N, such that n and m are equal. And similarly for inequality. So because they're predicate symbols of arity 2, they have to be interpreted in this structure as binary relations on the domain, and they are. So we're all done. So we can observe that this structure does meet the definition of a first order structure, and similarly, if you go back and look at the outline of the first order structure I gave in my song language, you'll notice that that meets the formal definition as well. As long as my song collection is non-empty, you can observe that all the constants, functions, and predicates have the correct type. And that's really all that the definition says. It says that the first order structure means picking a universe and then interpreting all the function symbols as functions of the correct type, in meaning that it respects the arity in that universe, and the predicates are all given interpretations of the appropriate arity as relations in the domain as well. Okay, so just as a kind of cooling down exercise, this is pretty much the end of the material, but I thought that it might be useful for you to be given some exercises in translating first order logic back into English for some kind of custom language. So here I've taken sentences from the first order language that I gave for my MP3 song collection. And I think it's interesting just for you to think about how you might translate these sentences back into English. Just as one example to help you get started, I'm going to take the fourth one. I'm going to take this one here. For all y, if y tilde 007 Shantytown, then tick y. Now remember that twiddle, I'd said, means similar to. 007 Shantytown means that song, 007 Shantytown, and tick means I like the song. So for all y, if y is similar to 007 Shantytown, then I like y. In other words, a kind of less clumsy way of putting this in English is, I like all the songs that are similar to 007 Shantytown. So I think it would be interesting for you to think, just as a little exercise, about how to translate the other ones here. Okay, so that is pretty much it for this lecture. So in today's lecture we saw how to give an interpretation for all the functions and predicate symbols in a first order language. And then in the next lecture I'm going to explain how we can extend this to give a truth value to every formula given some first order languages being either true or false in a particular interpretation, in a particular first order structure. So I hope you're looking forward to that. I know I am. And until next time, take care.